let's start. So this week is the last week for the semester. So we have only two lectures left. One is for this FFS and then crash consistency. So that's kind of the end of this lecture. Okay, so we're almost there. So let's finish it. Why does it take so long to download it? I don't know what's happening. Hmm. Oh, hold on, folks. I think I have some technical problem in my iPad. So let me fix. Right. Let's begin. Okay, so this time we are talking about a fast file system. So this lecture providing good example of how systems research work. So this lecture is talking about how to improving file system from the past file system, which was Unix original FS. So Unix file system having some pathologies, performance problems. So to improve this Unix original file system, FFS comes. So in this process, you need to do some technical conversation, which is like it's like a writing a paper. So you have to observe problems. Then what you have to do is providing evidences. So what this so here are list of problem and showing some quantitative evidences by measurements. Then, so people, this is kind of important process to persuade people. So after showing some evidences, very experimental evidences, then you can actually bring up new design idea. So you can actually kind of make an idea, and then how to demonstrate that your design idea is correct. How to prove it? Okay. Actually implement your idea. consequence of this implementing your idea is actually this fast file system. Okay, these are typical process of computer systems research, where you have to learn some system and then find some kind of inefficiencies and problems. Then you have to do like this process to that people okay. It's like your conversation of these things make sense in high level, and you correctly implement it, prove it, then your paper accept. Okay, that's high level process. And fast file system. This slide actually showing the example. So first thing is in introducing the original file system, work this way and analyze three problems. Three performance pathologies. The first one is block size is too small. So consequently, transfer rate is too low. True, you have to show that by measurement. Second, FFS using free list, which is unorganized. So sometimes using this free list causing fragmentation, aging. So as time goes by, as system ages, systems is more likely to be fragmented, then performance drops. Prove it, show it by measurement. And poor locality. So poor locality is about how inode and data blocks works and how they are accessed. So poor locality causes some disk. It doesn't consider disk performance characteristics, so eventually causing very bad performance. So there's a room to improvement. Show it. Okay, three problems. So the approach is to measure these state-of-art systems and idea of building and providing idea to build better systems. Okay, the key idea is that redesign file system structure and block allocation policy to be disk-aware, disk-friendly. So when you design a file system, let's consider device-specific characteristics to providing better performance. The first thing, so these folks, three groups of file systems invent BSD file in fast file system and implement in BSD. Okay, so key idea is this one. Let's take. So the first question was block size is small. So this is according to block size. Here are disk bandwidth. So when block size is small, it only utilizes 2% of max disk bandwidth. It's really small. But as using more larger block sizes, you can achieve much better throughput. But what is the downside of using large block size? What is critical error? So if you are using large block size, then it causes internal fragmentation. But we have some knowledge to deal with this internal fragmentation from the malloc. What's that? Splitting. So malloc having some idea of splitting. So instead of the allocating block in large, it has internal allocation unit, which is called fragments, which is smaller than block size. So file system allocate blocks, large blocks, but internally when allocate a file, logical file blocks, then it's allocate based on the fragments. So fragments is configuration parameters. So when a file system start, you can actually kind of fix. So you can set up the, given the block size, you can define the number of fragments per block. Okay, so it providing that, for large files, the block providing better performance, and using the fragment-based allocation, reducing the waste of space for small files. Here is the idea. So for this one, this is a fragment. So fragment size is 1 kilobyte and block size is 4 kilobyte. So when application read, the entire block comes to operating system page cache and read it. But when operating system allocate blocks, allocate of file data, but the allocation unit is fragment, which is 1 kilobyte. So this block consists of three fragments. 2 fragments belongs to this file B, and this 1 fragment belongs to this file A. and this block. So you are, when file increase size to 1 kilobyte, then this new fragment is allocated to this file A. Okay, and then here. And then if file keep appending to file 1 kilobyte, then FFS allocate new blocks, and this block is not used, and this fragment are assigned to file A. And keep updating. But once it allocate new append 1 kilobyte of fragments, then it turns out 4 fragments, which is 1 block size, are made. Then FFS migrates into whole entire block. Okay, so that's the operation of fragment. So because of that, small files still using 1 blocks, and maybe the other files can allocate this small fragment C, so it effectively reduce the internal fragmentation when using large block. Okay, so that was the idea. Second, so we stopped there, here last time, and then let's continue to talk about, next problem of FFS. So FFS using FreeList is natural. Original file system using FreeList. It's natural decision. Well, linked list, linked allocation. We learned an FAT. It's like a FreeList based allocation. However, using the FreeList allocation, initially you can actually searching the next blocks by traversing this FreeList. But when systems get over time, then this can be fragment. Consequently, you have to jump large blocks by blocks, large number of blocks to sequentially access this one. So to having a good performance, you need to sequentially allocate to reduce the fragmentation, to reduce sequentially allocate. But this FreeList is not that good data structure for sequential allocation as time goes by. So consequently, when you first purchase and then you reformat the file system, you can achieve 17% of disk bandwidth. But a few weeks later, you can only achieve 3% of disk bandwidth because of this, non-contiguous allocation in disk space. We know answer, but so they're proposing new data structure to manage block allocation. Okay, I'll get back to your question soon. So what was the data structure used for reducing this fragmentation? What was popular data structure to reducing to continuous allocate blocks? What was that? What is the way to managing free blocks in modern file system? Bitmap. Okay. So changing data structure, instead of using the FreeList, Bitmap. Oh. Hold on, please. Sorry, folks. Okay, so bitmap. So bitmap, each bit indicate whether block is free or allocated. For example, this is a sequence of bitmap where this one indicate block number 0. So 1 means allocated. This is block number 1. 0 means not allocated. Okay, so this entire bitmap are stored specific location. Here, inode bitmap or data bitmap. It's bitmap for inode allocation. This is bitmap for data allocation. So this bitmap easier to find the contiguous block. So I want to find the 3 contiguous blocks, but you can scan through the bitmap and finding these 3 blocks are blocks are contiguous and not allocated. So just kind of simply scanning the bitmap, you can easily find in contiguous block. Therefore, if you are using the bitmap, it's much better for allocate blocks contiguous much better performance than using the free disk-based block eventually. Okay. And also good performance benefit is the bitmap size is really small, right? So bitmap size is this small for 4 GB disk. And so you can load this bitmap into memory. So every time you allocate it, you don't need to write the bitmap in the disk because they are cached. Okay, so we can quickly access in the memory operation. That's the second idea. There was question about fragments. So let's go back to fragment. First question, how does fragments differ from just allocating small block size? Good question. So when you're reading a block, if you are using the small blocks, your block size was small. So block is minimal unit for reading and writing. Okay, so when you are reading a block, you have to reading 1 kilobyte blocks. But if you are using the 4 kilobyte in fragment is not the unit of light. So file system, you read and write entire block. Okay, so small block cases, you have to if you can your block size is 1 kilobyte, you have to read 4 blocks to blocks versus in 4 kilobyte block you just read 1 block. So therefore, using large block is much better performance. Any questions, Young? Second question. Then we read with some blocks contain A and B. Does protection? Okay, good point. Okay. Then how to partially free blocks? Okay. Protection. Okay. You're right. Okay. So let's get dive into more about this design. For someone actually say that 2 different files are located in the protection. Same blocks, so it may violate protection. Here is still for this case, it does not support a map-like system. But operating system maintain page cache A and page cache for B. Okay, the different file system. After permission check, it can access page application A, process 1, process 2 can permission check and access page cache. Okay, so the protection is enforced on page cache unit. So when you're reading on this block, operating system put this B block to this page cache, A block to this page cache. So operating cannot read this raw block, but operating system kind of separately copying this fragment to different page cache, and page cache has unit for protection test. So this design is okay for protection. Does it make sense? I mean, I don't want to go this detail, but yes, that was the reason. Does it answer for your question, Jian? Okay. There are follow-up question. How to present partially free blocks in case of 2 blocks used A but left 2 kilobyte free? Yes. So internally, instead of more than the bitmap, FFS maintains the separate metadata to maintain that 1 blocks having a free blocks or not. So there are some separate metadata to indicate which fragment are freed. So I don't go add details for here, but definitely FFS some separate metadata for free fragment in a block. That's also kind of hierarchical bitmap, but let's not talk about that. Okay. All right. So that's the that was the fragment example, and here is kind of a free list example. All right. So bitmap. Third thing is kind of most important influential design. I think this is actually the art of FFS, which is about port locality. So this is original FFS, when you are reading a file, you have to reading inode and data blocks, right? So reading inode first, and inode has index pointer which pointing to block location. You read it. Okay, so inode and data has to read at the same time usually, right? When you're reading the blocks. However, files. So this is kind of important kind of observations, right? So in some case, these blocks are spread out in data blocks, and in some case these blocks are very close, far, close, far. It may be possible. Okay, close, far. Okay. Given that, let's take a look at this thing. Files usually something as system ages. What's the blank? What I'm talking about? This symptom. Files are what? File blocks are what? What happened? Fragmenting. Scattered. Fragmenting. Okay. Blocks are allocated randomly over disk. This is inevitable. If you are using hard disk like a few months, then allocation, deallocation, these patterns kind of interweave. Then eventually your storage disk, your storage file system get fragmented, get scattered. Okay. So there's a case where inode are allocated far from the blocks. So this distance between inode and data blocks are far in some cases. Okay. And also files in a directory are typically not allocated in consecutive blocks. So if you look at the file, so directory, so say /A, /B, /C, and there's a file 1, file 2, file 3, and C, file A, file B, and file C. Usually, in case of special locality, the files in the same directory access together. But when disk is fragmented, these blocks are located far, so therefore they are allocated sort of far each other. Blocks for file 1, blocks for file 2 are allocated very far. So I'm talking about keep far in disk distance. Why far blocks matter? Why does it matter? Why far is problem? Why does it matter? Okay. This is related to this time. So this is new slide edit, but if you look at the storage slide, I added this one. Just for explanation, I just kind of added. So if you look at the hard disk, there are some kind of 3 important factors that affect performance. So hard disk is like this kind of spins, and when you are reading a file, you have to moving through this is called disk the mechanical motor that's moving around this tracks. So if you want to locate it block 20, ARM has moving around this one mechanically, and this disk spins to access block 20, for example. So this ARM moving time is called seek time. Okay, and rotational delay. There's a motor inside motor that actually kind of spinning, so rotational delay. Then these blocks, these sectors are copied into buffer and going to host system, going to CPU through DMA operation. So they're called transport time. Among 3, seek time, rotational delay, transport time. Which one takes the most? Obviously, seek time. Okay, seek time is the slowest. This is kind of electron movement. Movement for electronics, right? Rotational delay, the motor is really fast. Seek time is also slow, but this one is kind of mechanical movement inside disk. Imagine that how slow it is. So reducing seek time is most important for when you are using hard disk. Seek time is disappeared in SSD. That's kind of innovation. So SSD innovation comes from eliminating this mechanical time, seek time and rotational delay. But at this time, FFS design is the era they're using, people using file disk, hard disk. So considering these performance factors, why allocate far matters? Why does it matter? If blocks are located far, then cause it long seek time. Okay, so FFS design, designers noticed that there was kind of lots of seek time happens for when disk fragmented. How to reducing the seek time is the key question. What's your idea? Any idea? This is question, right? This is known problem. So, any idea? In case of SSD, I know the allocate far from blocked does not matter. Yes, it also affects some performance, but it does not matter. It does not much matter like hard disk. Much better case in case of SSD, because it does have like this seek time and rotation delay. Okay, so going back to question, any idea to eliminate seek time? What's your idea? Okay, so if you can allocate kind of inode and data in the same sector, that's fine. Okay, so initially trying to allocate inode and data in the same track. That's the idea. So do you remember that FFS is what? Disk aware. More specifically, it awares disk geometry. Okay, that leads to this question. There is a cylinder. So every time this is kind of an inquiry seek, right? And if you look at the hard disk consists of several kind of platters here, and grouping this one geometry and group it together, because allocating sector here does not, accessing this here does not require seek time. So using this information, you can allocate inode and data into cylinder group. So let me specify this. It is called clustering. So FFS folks allocates sequential blocks into adjust sectors. So it's if you access one blocks and probably access the last. So to avoid seek time, and try to keep inode and data into same cylinder. Okay, and tries to keep all inode in directory in the same cylinder. Again, as I say, if you usually kind of type command like this one, ls-s, then the files in the same directory access together. Using this locality, if you allocate blocks and the same files, when you allocate the files, you can allocate kind of sectors located in the same cylinder. So given that this information is exposed to a file system knows that some blank numbers located in this cylinder, some blank numbers located in this cylinder. You can discern the differences between sectors into different cylinders. That comes to this file system organization. So each block group pull all data structure and with each cylinder. So this cylinder group having effects of this on this layout design where these block groups, block groups, block groups. Okay. So still, surprisingly, modern file systems like Linux also affect this FFS design. So they managing different block groups. Okay. Block group, block group, block group. This is kind of LBA. So LBA is logical address space where the file or logical blocks are contiguously allocated. Okay. And block size is increased 4 kilobyte, as I say, large blocks. And super blocks are, replicated for reliability reason, but let's not, consider this kind of thing. So here are block groups. In each block group, there are some kind of, this substructure where super blocks, inode bitmap, data bitmap, inode, and data blocks are located. So these are kind of consist and block group. Then what you have to do, allocate block groups like this way. So each block group are located in each sector. Map block group to each sector. So when you access file, putting them into same block group. Therefore, inode for this block group 2, free space bitmap for block group 2, and data and directories are located in the same cylinder. So likewise, inode and free space in data blocks are located in the same cylinder. That's the FFS geometry, disk-aware allocation geometry. Okay. So these are kind of other things, balance directories and across groups. So they actually kind of partition namespace to balance across different block groups. Okay. And files and directories are accessed together. I explained that. So place together in the same cylinder to reduce time of 6. Okay. That's correct. Okay, so that's it. So that's the kind of art of FFS. So FFS first using the large blocks and fragment IDR to for locating and reading performance. So large block providing the performance and using the bitmap for contiguous allocation and using this block group for disk aware or disk aware block management, which is called cylinder group and block group. Okay, so consequently, they demonstrated run same application in original FS, original Unix file system and FFS achieves much better disk bandwidth compared to original bandwidth. Done. End of story. People like it, accept paper, and people kind of adapt this FFS design into modern file system. Okay, that's big success of files FFS story. Clear, right? So that's the end of the FFS and keep basic the story of a file system. And before moving to the correct consistency, which is last lecture, any questions? Okay, so all right. One thing. So students worried about the final exam. So how to prepare the final exam. So I told you that I I prepare some example questions. So here's the example questions that I can show you. Let me unshare first. Mm. Mm. Okay, so these are sample questions. Again, I put this slide into Piazza, so you can actually kind of download it. So here are some of the sample questions. The first type. So it consists of three types. First type, true or false. Okay. So here's kind of questions. For example, process. This is simple kind of questions, right? Process is protection unit. You can just kind of answer true or false. Okay. Sending IO command IO device is non-privileged instruction. For example, true or false? True or false? Recall that. What was that? True or false? False. False? False? Accessing your device is non-privileged, privileged. Accessing the hard disk is privileged, non-privileged. Privileged, non-privileged. True. Okay. Oh, sorry. Sorry. False. Okay. Oh, confused. Okay. So segmentation fault is an exception. True or false? True or false? True. Okay. So questions like this one. So in round robin, shorter time slice better than longer time slice for turnaround time. True or false? Round robin, time slice. False. Okay. Because context switching. Okay. So you can easily find it. So true or false is kind of a mixture of some basic things. So just if just look at the slide, you can just kind of write answer immediately. But there are some kind of tricky, some kind of hard questions I mix it for or just difficulty. So this the true and false are the first type, simple. Second one. Second one is kind of most hard. And one is kind of one of the I don't know. They are the similar type. This is also kind of a true or false question, but here's kind of thing. If you can look at these two code, whether this code work correctly or not. Okay, so looking at this code and compare that, this code doesn't have a liveness guarantee or safety guarantee, true or false. Okay, or if you can change some kind of operation, what happened? So this understanding the bugs of existing implementation. That's second type. Okay, so this kind of thing is a synchronization. When you understand the synchronization, this type of question usually kind of how to understand the knowledge of how the synchronization primitives, how to construct the system with the correct synchronous primitives. So this one is kind of asking that aspect of understanding. Okay, true or false, and giving the code. So this is type one. Second question is, I think, kind of most difficult, and having a low score, considering my past experience. It's hard to understand what the goal of the code is, though. Yeah. Okay. So this one is kind of the code for old lecture. So we never use these examples. Obviously, I can give this kind of example, but this is kind of too much milk problem. I teach in the previous old slides, but don't care about that. But this is just kind of one example. Second one is hard one. So this is most difficult. So you have to choose all true statement. So I can give you some kind of a bunch of questions, and you have to pick all the true statement. No partial score. Okay, so that's make this question really difficult. So the type two is more like you have to thorough understanding of kind of entire picture. Okay, so maybe I can actually kind of some things that I explain in the lecture and then put bundles together, and you have to pick only correct statement and no partial score, all or nothing. Okay, so hard one. I know this kind of question is evil, but I want to kind of respect the student who really study hard and thoroughly. So this question is kind of targeting very thorough, understanding, complete understanding of some matter. Okay, so that's the type 2. Third question is simple, short answers. So for example, compute average time, compute turnaround time, what scheduling metric SJF improves over FIFO, or moving processes between CPUs costly due to something and something, explain that, or describe 3 important problems of segment-based translation, or some code some code, this one, some code snippet is given. So there are some kind of example code given. You have to reason that this code has bugs or not. If it has bug, fix it. Okay, so this question, I always kind of prefer these questions. Okay, so that's the 3 types of question. 3 types of question. Can you tell me the portion of each type of questions? It depending on. Usually, in past example, 40% true false, 20% all choose, and 30% short answer. Interesting thing. What is kind of at least expected score for this type of question exam? Expected score. What do you expect? Right? So average score, it's not easy. Average score was 32, 40 was average. Meaning that exam is not easy. Okay. So 30 to 40 was the average score. I am trying to make this exam a bit easier, but that's my idea number. 40%, 40, make kind of average 40 is my goal. So exam not like easy this one. This is too straightforward, right? It's a bit harder than 2%. And again, these are final, and before starting the final exam, we will have PINTOS quiz like this in the previous PINTOS quiz in front of computer. So you can actually open the safe browser and take the PINTOS quiz exam for 1 hour, and followed by this exam question, which I will giving the prints of the exam, final exam question, and you just kind of mark your answer and submit to TA. Again, to prevent building a history, I always take these exam questions and I just kind of crash after taking the exam. Okay, there are a bunch of questions. Will there be any questions require calculation? Yes. Calculation. But not kind of, not like complex math, just kind of simple calculation. Yes, it may include like this one. If I decide to make this kind of question. So it may. And no descriptive question in final exam. Yes, but yes, because considering that we have 2,240 students, and people actually describe different way, so it's really hard to how can I say grade. But I think this type of question is harder than describing, because you have to clearly understand the point. So yeah, no describe questions. How will the ratio will be similar at this time too? I don't know. Because I need to adjust some time because previously we have 3 hours, but this time we have only 2 hours. So 1 hour PINTOS quiz, 2 hour final exam. So I may kind of reduce number of questions at this time. So that actually affect kind of a bit adjusting the ratio. But I want to kind of make a large true false questions still this time. But it's not decided. Will the exam time or text time? No. Oh, depending on your understanding. So some students who are actually kind of look at the material very thoroughly, true false time questions not very hard, but some these questions you can think about some possibilities and cases. So usually because it does not describe and complex computations, looking back the past final and then midterm exams, it was not time usually. Any other questions and concerns? Will you please making the final exam before making the final exam before Pintos quiz if everyone agrees? Why? Why do you suggest that? Is there any kind of reason that taking the final first and then Pintos later? Ah. 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 Okay. For now, let's have a poll. So, so we have 140 students. So if you think, taking the final exam first and Pintos later, click yes. Final followed by Pintos, yes. Pintos followed by final, X. Please join the poll. Yeah, but let's see that. No. If it doesn't have big difference, then I will do Pintos and followed by final. Or stick to original plan. Please join the poll, folks. Come on. So taking the final first and then Pintos, click yes. Taking the Pintos quiz first and followed by final X. Come on, please join. Yeah, okay. So it's okay. So it seems like there's no big preference for taking the final first. So Pintos and final. I'll go to the original as I announced before. Okay. All right. Is there any kind of estimate schedule of claim for quiz and final? So yes, TAF preparing for the claim time for Pintos and final estimation. I'm not sure, but I think right after finishing the exam period, I guess. So 2 weeks later. But definitely we will announce the claim. So we have enough time for claims. So if you have some kind of schedule problem, please feel free to post it to Piazza so we can make just the claim time. Any other questions about final? The room will be reserved again for did who? Yes. So yeah. So that was kind of problem that we don't make a kind of the computer room for students who are having a trouble for accessing the safe browser. This time we prepared, so we resolve a room, a computer room for Pintos quiz. So no worry about that. Concerns? Okay. All right. So let's moving to the final topic, crash consistency. Last one. Okay. Can you explain the difference between using the linked list and bitmap? Is there pros and the pro point of bitmap allocating file contiguous block? Oh, yes. Because it easily find the contiguous block. Yes. Bitmap based allocation, you can easily find in contiguous block. Just scan through the bitmap and finding free contiguous blocks is easier. So when you're allocating free list based allocator and bitmap based allocator, operating system more using the free contiguous chunk, so systems are less likely for implementing. That's benefit. Okay, so crash consistency. So crash consistency is unique topic for file system because in DRAM, data is volatile. So any order, any sequence of data, you can actually kind of, after booting the system, you have to reload it to DRAM. But hard disk and SSD are persistent store, and for performance, file system designer typically putting data into cache and persist later. That was basic model. Loading data into cache DRAM and persist later. Okay, so existence of these two cache DRAM and persist later cause crash consistency problem. So crash consistency, so this is new requirement, new unique design requirement. For okay. File system may perform several disk writes to complete single system call. Recall that several disk writes. Why this slide say several? For example, what are examples? What are examples? Okay, one example is saying a file is larger than one sector, the other one. Let's say file is even file is one block. When you are complete system call, you have to perform several disk writes. Do you recall that? For example, what? Why several? And why more than two? inode and data block. So they are located in the separate sector. Therefore, it causes several disk write happens. Okay, because of that. So for understanding of this one, let's say this is file system state. File system state. State is ambiguous term, but state is kind of describe. How can I define it? So I just keep using state without any kind of formal definition. State is kind of the required information to run the file system. There are kind of inode states and data blocks and these directory blocks, bin maps. These are file system state. Okay, so crash consistency formally you can think about the case where in-memory state and on-disk state. Within that, in-memory state are synchronized to on-disk. So in-memory state has up-to-date information, and on-disk state is state information because your modification, inode updates, and the new directory blocks apply to in-memory state. And that has to be persisted to on-disk, but consistent way. So system interrupted between several writes. So then on-disk structure may be wrapped in inconsistent state. So I need to define what is the inconsistent state. State, I'm talking about these data structures. I know data, the bitmap, superblocks, and when again the disk only performs single sector. So single sector entire itself is entirely applied to hard disk or not. But if you can make a multiple sector writes, then between the sector write, it may not. So in case of power crash, so we want to write inode block and data blocks, but power crash happens in the middle, then the following, the data block writes, the second write may not be persistent. So event like power loss, system crash, some transient hardware malfunctioning, your hard disk sometimes kind of power off and power on again. So these kind of events cause some kind of blocking. So in-memory states are persisted in some order, and only one updated, the other one is not. Okay, that is the case, possible case. Even that consistent state has to, disk state always has to be consistent. Here, consistent is that inode and data are metadata. Inode is metadata of data. So if inode say 10 blocks and data block 10 block must be exist. Inode index pointer pointing 10 valid blocks, then 10 valid blocks has to be exist. If inode bitmap says inode 1 is not allocated, then inode 1 has not used actually. So I'm talking about consistency between metadata states between them. Don't get confused. I'm talking about consistency between inode information and actual data block states. Consistent between bitmap and inode states are consistent. So crash consistency is not about preventing data loss. Data may lose. You may lose data, but inode and data state has to be consistent. Okay, so still a bit vague, so let's make it clear. So let's show this example. So let's say these states, on disk state. So 3 states I'm talking about: inode bitmap, data bitmap, inode, and data blocks. This is initial state. And when you are appending a new block, in on disk in memory DRAM, I'll say in memory, new data block and inode prime and data bitmap is updated. Okay, and then they are persist into on disk. Then this information has to be consistent. This information and this information has to be consistent. Okay, so that's the definition of crash consistent. No matter how. So for example, when you're updating inode, crash happen, but on disk having a consistent state. That's definition of consistent. So typically you can analyze this case. So 3 things are bitmap B, inode I, and data directory D. Okay, so these are original data. So let's say you can say this is on disk state. And these are new states, in-memory state, updated by file system, have to be applied. So 3, distinct write happens in some case, right? For example, new blocks are located, okay? Or new inode is allocated, or you can append the new blocks likewise. So you are writing BID. However, when you are persisting this data, file system persisting this data to disk, again, there is a crash in the middle. And operating system internally reorder. So for performance, IO scheduler in operating system, the block buffer, reorder it. So given that, you want to kind of update BI prime, DI prime to persist disk. What are possible permutations? How many permutations possible on disk state? So you're updating. How many? These are possible cases. So first case, no applied. First one, block is updated, but inode and data has to be remain same. Is remain same because you are writing a block and inode block is not updated because of crash. This case, only inode is updated. This case, data block is updated. This case, bitmap and inode is updated. This case, bitmap and data blocks inode are updated. So more thorough reasoning is that you have to consider case where inode, bitmap, and data block, but for convenience, that's kind of merging into one bitmap operation and see that. So these are possible cases, and every case consistent. You have to check whether this on disk states are consistent or not. You have to analyze it. Okay, so that's the first understanding of crash consistency. So let's take a look at scenarios. Oh, is parent directory of inode length also updated? Yes. For parents directory inode length also can be updated when you're adding a new file. Inode length, parent direct, what's the specific case in your question? Length attributes updated. Yes, if new inode this or new directory blocks updated, then the inode length for directory block updated. But I'm not talking about what's parent in your case. So could you elaborate it? Since directory data is appended, so maybe 4 parts should be updated. Yes. Well, precisely. This is a more simplistic analysis of crash consistency, but actually, we're talking about the parent inode, considering the parent inode, but let's kind of simply analyze for this case first. A real crash consistency of bitmap and superblock, this is much more complicated. But for educational purpose, we make it slim down and much more, make it more easier. Okay. So here's first case or crash scenario, no problem. So there are cases where all data touched, no problem, obviously. So inode say length. Inode say I have 2 blocks, 1 and block 1, block 1, 2, 3, 4, 5. I have block 4 and 5 says, and actually the data is persisted, and new data block 5 is also located. Good, so no problem at all. And nothing touched media, clearly no problem. Now let's take a look at only data blocks written. So new data blocks are written to disk. Okay, inconsistent. Inconsistent. Which case? Okay or inconsistent? Okay? Okay? Since it's okay? Yes. Why? Because no data point, no index which pointing to block 5. So, and data bitmap also says data block is free. So, okay. Only just kind of written to this. But this block, there is no inconsistent information in bitmap and inode. So, okay. So, writing the inode, this case, for okay. Second, updated inode is written. Okay, inconsistent. Okay? Inconsistent. What are cases of inconsistent? What are the cases? Inconsistent. Okay. So cases first, inode I pointing to data block 5 here, but this is garbage. And also, so when reading this inode, read it to garbage data. So all the contents of data block in here. Second, data bitmap says block is not allocated, but inode says data block is allocated. So inconsistent. Okay. Later, if data block 5 is allocated to another file because data bitmap says no block is allocated for block 5, and the same block will be mapped together by two inode. That's going to inconsistent. Okay, so this is clear inconsistent state. Third case, data bitmap is written. Okay, inconsistent. Which case? Data bitmap is written. Inconsistent, okay. What's the answer? Inconsistent? Okay. So now again, inconsistent, right? So data bitmap indicate data block 5 is allocated, no inode pointed. Consequently, data block 5 is never used by file system, so you lost space leak problem. You lost that data block, cause space leak. Okay. Fifth scenario. Let's make them a bit more complicated. Two cases. So inode and data bitmap is written. Consistent or okay, inconsistent. Tricky. Okay, inconsistent. What do you think? Yeah, but I'm asking though, inconsistent, okay. What do you think? Okay or inconsistent? Oh, you guys really smart, right? Okay. Okay. So maybe it read garbage data. Yes. But metadata states are consistent. So file system metadata is completely consistent. Yes, inode having pointer to data block 5 and data block indicate it is. So it read may garbage data. But file system define that this case, there is some data, right? So what's new data, what's old data, there is no way to distinguish. So in this case, file system define this state is consistent. So sometimes bad file system crashes, then you're reading some garbage data because of this problem. So inode and data bitmap is correctly persisted, but data blocks are yet to persist. So you may read garbage data. So this is the typical case. Okay. Okay. So third case, sixth case. Data bitmap is data blocks written, but inode is written, but data bitmap is not written. Okay, inconsistent. Okay, or inconsistent. Okay, so now things get easier, right? Inconsistent, obviously, right? So inode having some consistent information, but data bitmap is not. So what are possible consequences? Here's case. inode has pointer to data block 5, and data block indicate it's free. So data block 5 can be reallocated. So file system see that, oh, this block is not allocated. So another inode. So same blocks will be used by two different inodes. So inconsistency. Okay. Okay. So seventh case. Inode bitmap data blocks are written. So bitmap written, data blocks written. Inconsistent, consistent. Inconsistent. Is it problem? Because inode does not having a pointer for that. What's the problem in this case? clearly this case is inconsistent. What was the problem with this case? Okay, yes. So data bitmap indicate block 5 is in use, but no inode pointed. And consequently, data block 5 will never be used by other file systems, cause space leak problem. Okay, clear, right? This is simplified scenario again. In some case there are multiple inode updated, right? Like parents and child, or multiple, inode and data bitmap is updated. Okay, so you have to consider in real file system, you have to consider all the possible cases to build consistent problem. But just for understanding, basic understanding of the nature of crash consistency, I actually kind of giving this example. Okay, so looking at one example, let's say this consistency, we can resolve this consistency, right? Okay, so Haewon, I will get back to your question. This is kind of some design philosophy, but I will get back to your question. In this case, I will get back to I'll get back to your question soon. So first one, this problem may be solved. How to solve it? How to solve it? First of all, file system never know that this new block is new or old. Doesn't know. And inode says it only having a block 4. And bitmap says 4 and 5 use. How to resolve this inconsistent state? No, it's impossible because you don't know this block is correctly written or not. So updating inode is dangerous. Okay, so what's the consequence in that case? Remove unused. Okay, searching inode and see that, oh, inode say block 5, but oh no, there was no inode using or having a pointer to block 5, and maybe this is incorrect. You can actually fix it, right? So this operation called FSCK. So let me stop here. So the next time I will talking about in this case, given that crash happened and run this scanning operation to make this consistency operation, which is called FSCK. Then the most popular way to providing consistency called journaling, and that's kind of end of the crash consistency lecture. Okay, so this time you need to understand the nature of consistency, and you can see, analyze each cases and what are possible consequences. That's the one thing. Okay, all right. So there was question. Okay, so Haewon's question: why do you think reading garbage data is as a problem? But here are more like design consistency problem. So consistency is talking about these two states are consistent. Inode say I have 2 blocks. Inode says I have 2 blocks. Okay, and bitmap says this one. So for file system perspective, these are completely consistent. This information and this information. So file system define these states is consistent. You may like it, but at least this is not violate consistency guarantee. Evan, does it make sense? So yeah, okay. Okay. Follow-up question. In SS case, since in-place obturation is not possible, can crash scenario is problem? Good question, So here, is it actually flash cell or LBA? What I'm talking about? I'm talking about LBA space, space or flash cell. Which case? Here, LBA. So if you can update it in place, the logical placement is completely safely done by FTL. So file system perspective, you don't care about in-place update. Because this operation transparently, if you can in-place update, FTL actually allocate new blocks underneath, which is not our concern. It's hardware thing. So what I want to do is only kind of how to placing data, how to make this data in LBA space consistent. So it doesn't matter. Does it make sense? Okay. All right. So next question. What was the next question? Can you explain the question, Piazza, about order violation? Oh, sorry. I didn't read these 237 questions. I will get back to. I will actually post it to Piazza. Okay. So yeah, order violation. And any other questions? If data bin map and I know the updated, will there be no inconsistency regardless of updating data blocks? No. If I know data bin map and I know bin map and I know the correctly or consistently updated, then there's no case in inconsistency. Any other questions? Okay, so this is clear. Okay, so let me stop here and let's continue to talk about crash consistency in this last lecture in this Wednesday. Okay, thank you. I'll talk to you this Wednesday.